My name is Brody.
My name is Gavin.
My name is Madelyn.
And my name is Zach.
The following video will demonstrate an extremely sped up simulation of the Big Bang that is theorized to jumpstart the universe as we know it. So the time period that this is taking place in is the predominant era, which is the first of 5 eras predicted in the Big Bang Theory.
In this speech, we will cover what the Big Bang Theory is, what evidence there is to support it, what the theory predicts about the future, and other contrasting theories.
Many of you may have heard about the Big Bang Theory. Maybe the first thing that comes to mind is space or the universe. And those are both correct, except for the theory entails so much more. According to Oxford Languages, the definition of a theory is a system of ideas intended to explain something, especially one based on general principles independent of the thing to be explained. Well, the theory was created by Georges Lemaitre, who was born on July 17, 1894, and died on June 20, 1966. According to FSCJ, he was a Belgian Catholic priest, a mathematician, an astronomer, and a professor at the University of Louvain. He was the one that officially formulated the Big Bang Theory. According to NASA, the theory states that the universe originally started as a single point. That single point expanded to where we currently are today, and it is still expanding. Within this single point was hot and extremely small particles mixed with light and energy. Those particles then grouped together to form atoms. The atoms grouped with other atoms forming clusters, and as more atoms combined, different elements were formed. Grouped elements led to stars and larger forms of denser mass. As the cycle went on, galaxies were formed, and they were also crashing and grouping together. New stars were being born and dying, and things like asteroids, comets, and black holes were created. Scientists have discovered that the universe is 13.8 billion years old, so that's when the Big Bang would have occurred. Brody will go into more detail with the technology, the multitude of advanced technology that can prove this theory. There are 5 Big Bang Theory eras: Primordial, Stephanus, the Degenerate, and Black Hole, and the Dark Era, according to Florida State College at Jacksonville Press Books. The Primordial Era is the first era that happened very early on and is a much shorter period compared to the rest of the eras. So this would have happened in the very beginning right here. It includes the actual time of the Big Bang as well as the immediate actions after. The Stephanus Era is the current era that we're in. Matter is arranged in the form of galaxies, galaxy clusters, and lots of energy produced by stars. By the end, bright stars will be gone and their nuclear fuel exhausted, with only white and brown dwarfs as well as black holes left. This brings us into our degenerate era. The degenerate era is brown and white dwarfs with black holes left. However, the white dwarfs stimulate dark matter and continue with a nominal energy output. As the era continues, protons will begin to decay, and if this proton decay takes place, then the sole survivors will be black holes. This leads directly into the black hole era, which is around here. The black hole era is organized matter and will remain only in the form of black holes. Black holes themselves slowly will evaporate the matter contained in them, and by the end, only very low energy photons, electrons, positrons, and neutrons will remain. Lastly, we have the dark era. The dark era is when there's only very diffuse matter that remains. Activity in the universe will decrease dramatically. Low energy levels with large timescales, as well as electrons and positrons floating in space. Sometimes the electrons and positrons will find each other and they will form a positronium atom. However, everything is so spread out that this will be a rare occurrence, and the gravity and gravitational pull will rarely affect each other as there's nothing to orbit or pull on. The universe will be a desolate and isolated place. Now, Brody will come and explain some of the evidence as well as technology used to find how this Big Bang Theory actually occurred.
So with the Big Bang Theory, there are 4 main pillars that support it: the spiral nebulae, Edwin Hubble's law, CMBR, and nucleosynthesis. These are the main points supporting the Big Bang, and that make it the most influential and well-supported theory. In 1912, a scientist by the name of Vesto Cipher calculated the speed and direction of spiral nebulae. By measuring the change in the wavelength and light coming from it, he realized that almost all of them were moving away from Earth. In 1924, Edwin Hubble used a research method constructed by Henrietta Leavitt to track the distances of remote objects in the sky. Hubble used something called spectroscopic redshift. This measured the speed the objects were traveling along with the distance the objects were away from Earth. Hubble graphed these two sets of data and realized the astronomical object's speed at which they were traveling apart is proportional to their distances from each other. This was later called Hubble's law, and as you can see, here's a graph of it. The distance is directly proportional to the velocity. In 1996, two guys by the name of Arno Petzas and Robert Wilson tried to develop a device to detect radio waves. They were receiving a bunch of interesting information and thought it was from a nearby city, but they later realized it was from outside the galaxy. Cosmic microwave background radiation was discovered, CMBR, and it was leftover radiation from the initial Big Bang. In 1992, a satellite called the Cosmic Background Explorer was launched, and then in 2001, the Wilkinson's Microwave Astroscopy Probe spacecraft, the WMAP, was launched to more accurately track the data. After 9 years, the WMAP provided a detailed temperature map of space, and it indicated the patterns of radiation, supporting the theory that the universe started off dense and expanded. As you can see here, the orange spots are the hottest spots, and the dark blue are the coldest. You can see it's evenly spread out and supports the theory that the universe expanded. Lastly is nucleosynthesis, which is another piece or pillar of evidence. Scientists looked out into the universe and took ratios of elements such as hydrogen and helium and other trace elements and realized that if the universe was one big star and it exploded, it would come out the same. Now I have an experiment for you guys to more accurately show Edwin Hubble's law. So before break, I passed out a rubber band and a balloon. With the rubber band, I want you to match up a few of the marks on it to 0, 1, and 2. Wait, hold on. And as you can see, if you stretch the middle mark to 2, the last mark will stretch to 4. And that will work with everything. This supports Hubble's law that the distance from astronomical objects is proportional to the speed they move apart. Now Gavin will explain what this actually says and what it will predict in the future.
So based on large quantities of experimental observation and theoretical work, the scientific consensus is that space itself is expanding, and has been expanding very rapidly within the first fraction of a second after the Big Bang, which occurred 13.8 billion years ago. This kind of expansion is known as metric expansion. Thanks to a man by the name of Edwin Hubble, we're able to know just this. Now, you might recognize this from the famous Hubble telescope, which was named after the American astronomer. As Brody said earlier, Edwin P. Hubble confirmed that the universe is expanding, which provides a foundation for the Big Bang Theory, as it can show that everything is expanding and still moving off of that same energy produced from what we call the Big Bang. By 1922, Hubble had completely reimagined our place in the universe, both by discovering and proving millions of other galaxies through his research, but also by demonstrating the universe itself was expanding. Contrary to the previously held belief of a static universe, Hubble ultimately demonstrated that galaxies are moving away from us. By studying the light emitted from various galaxies, Hubble's discovered that light appeared displaced towards the red end of the spectrum. His work proved the universe has no center and everything is moving away from everything else, which was also proven by the phenomenon redshift, which reveals that the further the galaxy is away from us, the redder their light will appear. Hubble also demonstrated that galaxies further away from us are receding faster than those nearby, a fundamental observation known as Hubble's law. This was some of the earliest insight into the origins of our universe and gave key evidence to support this theory. Now, if this statement is true, what does this mean for the future of our systems of galaxies? While as astronomers and mathematicians have looked into the end of our universe through this lens, there are two main ways this universe could end. The cosmos could eventually collapse back in on itself or continue to inflate forever. Exactly how the universe might end depends on the rate of cosmic expansion. Bethe states that if gravity overpowers expansion, the cosmos will collapse in a big crunch. If the universe continues to expand indefinitely, we will experience a big freeze. But let's start at the beginning of these theories. In 1922, a Russian physicist and mathematician by the name of Alexander Friedmann derived a famous set of equations. These calculations showed that the universe's destiny is either to expand or contract, rather than remain in a steady state. Later, in the 1960s and 70s, when astronomers added up all of the matter in the known universe, they calculated that there was enough mass that the cosmos should collapse into an infinitely dense state, or perhaps even a gargantuan black hole. Some speculated that once compressed into this form, like the Big Crunch, the universe would kickstart yet another expansion, or the Big Bounce, starting over the events of the cosmos. So at the time, this theory was the most widely accepted for the end of our universe. A revolution in understanding black holes was underway during this time period, and some of the major scientists at the time saw each black hole as an experimental model of our universe's final state, believing that the same events could occur at a much larger scale. With enough matter, gravity would eventually halt the cosmos' expansion, causing it to crash back inward. However, in the late 1900s, two separate groups of scientists were surveying the distant universe, studying dying stars that helped to establish cosmic distances. They found distant blasts appeared dimmer and were therefore further away than expected. The universe's expansion wasn't slowing down at all. It was speeding up. These two teams have independently stumbled onto dark energy, shattering existing models of the universe. With this discovery of dark energy, it made it very unlikely that the universe would collapse into a big crunch. Gravity would never be strong enough to overcome the inflating effect of dark energy. In other words, the expanding universe is designed for a big freeze. Thanks to the expansion caused by dark energy, within a couple trillion years, the closest galaxies will be too far away to see. Then perhaps 100 trillion years in the future, star formations will cease, as stellar remnants like white dwarfs and black holes lock up any remaining material. So the reality of our universe is that it might be dark and empty, yet all starting from a tiny, dense fireball that has created everything we know today. Now, Zach will go into another possible theory that is contrasting to mine.
Another one of the most popular contrasting theories to the Big Bang Theory is the steady state theory. In cosmology, the steady state theory shows the view that the universe is always expanding but maintaining a constant average density. A steady state universe has no beginning or end in time, and from any point within the view on a grand scale, meaning the average density and arrangement of galaxies is the same. The steady state theory was first proposed by Sir James Jeans in the 1920s and was later boosted and completed in 1948 when Fred Hoyle, Thomas Gold, and Hermann Bondi reformulated this theory. There is a debatable story that they came up with the theory after watching the film Dead of Night. This movie ends the same way it begins, which led Hoyle to think that the universe could be unchanging but dynamic. The steady state theory, simplified, is saying that as the universe expands, everything else also expands proportionally, meaning the universe does not change drastically in appearance. This visual over here shows the difference between the Big Bang and the steady state theory and how the galaxies form when the galaxy is increasing. As you can see here, as the universe expands, so does everything else, and the density will get lesser and lesser. In the steady state theory, as the universe expands, more galaxies also increase, and the density will stay the same no matter how much it increases. One of the main differences between the steady state theory and the Big Bang theory is the steady state theory explains that there is no beginning or end in time. This means that the universe never started, it just always has and always will. Unfortunately, For this theory, there is more evidence against this theory than there is for it. For example, radio observations that were made that went far into the universe returned with informations from billions of light years ago, with evidence of a changing universe, which is basically the opposite of what the theory states. Although there is evidence against this theory, one of the main pieces of evidence for this theory is supported by something called redshift. The redshift explains that the universe is expanding at a constant rate and at an increasing rate. Distant galaxies are flying away from us, and the faster they're moving, the redder they appear. This is because when a wavelength of light is stretched out enough, the color of it changes. This proves that the galaxy is always moving, because as more and more universes are being constantly created, the galaxies would still be moving away from us, hence displaying redshift. Overall, it is a reasonable theory, but just doesn't have as much evidence as the Big Bang Theory. This is one of the main reasons it is less known and less supported than the Big Bang Theory.
Hitting it off, many people have a misconception about how the Big Bang actually is expanding the universe. Many people think it's from a central point, similar to pouring a glass of water on a table. Everything expands from that, or the water expands from that one point. But more realistically, it's like blowing up a balloon, expanding everywhere all at once and even stretching. Before break, I passed out this balloon, and feel free to draw a bunch of little dots on it. And when you blow it up, you can see that everything is expanding away from each other all at once and even stretching.
After doing research, our group has come to the conclusion that the evidence supporting the Big Bang Theory was more sufficient compared to the steady state theory, and that the Big Bang Theory is more likely to have occurred to start the universe. When thinking about your open-ended question, when you have to formulate your own opinion on about whether the theory is better, think about what you know about the Big Bang Theory, what evidence supports it, and what it predicts for the future, as well as any information about the steady state theory. If you ever find yourself looking at the stars or in science class, remember that it is possible that all of us are here because of the Big Bang. Thank you.
Thank you.
Thank
Thank
you.
you.